Good day, everyone. My name is Wenjian, and my student ID is MEC2409004. In this video, I will explain two tasks from my assignment. Task 1 is the implementation of a circular singly linked list, where the last node points back to the head node. Task 2 is the implementation of a stack using a singly linked list, which follows the last in first out principle. For the task 1, it is a circular singly linked list where the last node points back to the head node. There is no pointer at the end of the list. This structure allows continuous traversal of the list. Normal linked list ends with no, while circular linked list loops back to the first node. This is for the node structure. The data stores the integer value of the node, while the next stores the address of the next node. Using node instead of struct node, making the code cleaner. And this is the code for how the last node links back to the head. In our circular linked list, the last node does not point to node. Instead, the next pointer of the last node points back to the head node. In a circular linked list, the code defines the next stores the address of the head node itself when inserting the first node for the linked list, which ensures from the beginning that the linked list will be self-circular. And this is the function isEmpty. It checks whether the linked list is empty. If head is no, the list has no nodes. It will return 1 if empty, otherwise returns 0. And this is the function for insert node. It first checks if the list is empty and only position 1 is valid. Then the new node points to itself. This creates a single node circular linked list. If insert at beginning finds the last node in the list, update the last node to point to the new node and updates to the head pointer. The result is the new node becomes the head, then the circular structure is preserved. And for insert at the middle or end, it will traverse the list to locate the correct position and inserts the node between two existing nodes. If the position is valid, an error message is shown. And this is the function for find node. It will search for a specific value in the list. It uses a do-while loop to traverse the circular list. It will stop when it returns to the head node. And for the function delete node, it will delete the first occurrence of a given value, and it handles 3 cases: the single node list, deleting the head node, and deleting a middle or last node. For case 1, single node list, this case checks whether the list contains only one node. The condition confirms that the node points to itself. If the node's data matches the value to be deleted, the node is freed from memory. The head pointer is set to no. And the result is the list becomes empty after deletion. This is for the single node list. And for deleting the head node, the program first locates the last node in the list. The last node's next pointer is updated to point to the second node. The head pointer is updated to the next node, and the old head node is free. And for the case 3, delete a middle or last node. This case handles deletion of a node that is not the head. First, 2 pointers are used. The first one tracks the previous node, and the current tracks the node being checked. When the target value is found, the previous node skips the current node, and the current node is free. And for the function display list, It will display all elements in the circular linked list. It traverses the list using a do-while loop. It will stop when it reaches the head again. And for how to handle empty list. Before performing any operation, the program checks whether the list is empty. If the isEmpty function returns true when the head pointer is null, this prevents operations such as traversal, deletion, or display on an empty list. In displayList function, an if statement will be used to check if the list is empty. If it is empty, then print the list is empty and return the function. By handling this case early, the program avoids segmentation faults and undefined behavior. And for how to handle single node list. A single node list is identified when the node's next pointer points back to itself. The delete node function uses an if statement to check if the current head node points to itself, to determine whether it is a singly linked list. This ensures the list is properly reset and no dangling pointers remain. And for how to handle invalid position. In the insert node function, the code will print invalid position when the head node is new and insertion position is not equal to 1. In the insert node function, if the insertion position is greater than the total number of nodes in the linked list, it will be print invalid position. And this is the sample output. This is for the code in main function. And when the main function code is written like this, it will output the following. First, it will display that the list is empty, and then shows insertion of values 10, 20, and 30. Demonstrate the searching for existing and non-existing values. Displays deletion of nodes one by one. And then the final output confirms the list becomes empty. And this is for text 2. This code implements a stack using a singly linked list in C program. Each stack element is stored in a node, and the top of the stack is managed using a pointer called top. The program uses a menu-driven approach to allow the user to push, pop, count, and view stack elements, while dynamically allocating and freeing memory during execution. And this is why a linked list is suitable for implementing a stack. A stack follows last in, first out principle. The linked lists are dynamic, so stack size can grow or shrink at runtime. And no need to declare a fixed size, unlike arrays. Efficient insertion and deletion at the head node, which matches the top of the stack operations. In this program, the top of the stack is represented by a pointer named top. Top always points to first node of the singly linked list, which represents the topmost elements of the stack. Since a stack follows the last in first out principle, the most recently pushed elements must always be accessed first, and this is achieved by keeping it at the head of the linked list. And this is for the code explanation. Function add, and this function creates a new node with the given value. It says new node points to the top and to insert at the beginning of the list. So it updates top equals to new node. The result is new element becomes the top of the stack. And this is the function withdraw. It will first check if stack is empty, at which the top equals to no, then the stack underflow. Second, it will store top element's value. First, it will update top equals to top point next. Remove the current top node. Freeze, and it will freeze memory of removed node. Then it will return the withdrawn value or if stack is empty. And this is the function for display. First, it will traverses the linked list from top to node, and it will print all elements in top to bottom order. If stack is empty, print stack is empty. The purpose for this function is to allow user to visualize the stack contents. And this is the counting function. It traverses linked lists from top to node and counts the number of nodes. Then it will display total elements in the stack. It is useful to track stack size dynamically. Stack underflow occurs when trying to pop from an empty stack. It's detected by checking if top equals to node, then message printed, stack underflow, no elements to withdraw. Then the function returns -1, allows main program to handle gracefully. And this is for how the menu and switch case control program flow. This is the related code. And first, we use do while loop ensures the menu repeats until user exists. And then I use a switch choice handles user selection. When user choose case 1, it will use add function. And when user choose case 2, we will use the withdraw function. And we will use counting function when user choose case 3. And the code will exist when user choose case 4. And the default is invalid choices message. This allows controlled and interactive program flow. And this is the output explanation for choice 1. For case 1, add function. When the user selects add, the entered value is pushed onto the stack. The program prints a confirmation message and then displays the updated stack with the new elements at the top. And this is case 2, withdraw. When withdraw is selected, the program removes the top element of the stack. If the stack is not empty, the withdraw value is printed and the remaining stack elements are displayed. If the stack is empty, a stack underflow message is shown. And this is for choice 3. Case 3, stack count. This option counts how many elements are currently in the stack. The program outputs the total number of elements without modifying the stack. And this is for the choice 4. Case 4, exist. When the user chooses exist, the program prints an exist message and terminates. No further stack operation are performed. And for conclusion, the challenge I face is that I don't know how to implement a circular linked list first, and I don't know how to write a stack structure code at first. And I solved the problem by reviewing the course materials and search for some relevant information online to finally solve the problem. I benefited greatly from this coding assignment. I reviewed how to insert and delete nodes in a linked list, how to implement a stack structure using a linked list, and also learned that code needs to declare handling for special cases. In this process, my programming and problem-solving skills were improved. That's all. Thanks.